In this video, we'll look at graphing energy changes during a phase change. Sounds pretty wild and crazy, huh? A long time ago, we used to that was probably the world's most boring lab. We took ice cubes, put them in a beaker, put it on a hot plate, and we graphed the temperature change over time. Sounds pretty awesome, huh? And yeah, we'd get a graph. We were trying to get a graph that looks a little bit like this. A temperature versus time graph. So we'd maybe plot the temperature every minute or 30 seconds or so. As time goes by, heat is added. So we could put that down at the bottom. Heat, energy is added. And so initially everything was fine and dandy. As we put the beaker of ice cubes on the hot plate, the temperature would increase. Shocker, right? But then all of a sudden, the thermometer would hit 0, and it would stay at 0 for a period of time. And this would really confuse students because they'd think like, well, maybe my thermometer is dead, the battery is dead, I'm stuck at 0. That's not right. And so they'd switch out their thermometer, like turn up the hot plate. Maybe there's something wrong with the hot plate. Because if I still have this beaker of ice sitting on a hot plate, heat is constantly being added. So they expected the temperature change to constantly increase. And instead, for a period of time, the temperature was stuck at 0. And so they were really confused by this. And so then often, you know what kids would do? They'd fudge their data. And so they'd think that it was some kind of error. That they assumed they should get a beautiful graph with a positive slope, and there shouldn't be any of these plateaus in my graph. If I am constantly adding heat from the hot plate, then shouldn't my temperature constantly increase? I thought it was some kind of error, that the temperature was stuck at 0 for a while. Because then after time, it did start going up again. And then they'd be like, all right, guys, we're back in action. The temperature is increasing. We're adding more heat. And we didn't always go all the way up to 100 degrees. Or at least if we did go to 100, we didn't go for a long period of time. But the temperature would do the same thing. If you continue to heat a sample of liquid water, you're going to get a period of time where the temperature is stuck at 100. And you'd think that there's something wrong, because again, you are constantly adding heat energy from your hot plate or your Bunsen burner or whatever it might be. So how is the temperature not increasing? It really confused kids. We're going to do the same lab, but we're not going to do it right away. But by the time we do the lab, we'll kind of know what's going on here. When we look at this graph, I'm going to label some of these sections. So this bottom section here, let's call this section A. This first plateau, which happens to be at 0 degrees, let's call that section B on my graph. And then this middle section, you got it, we're going to call that C. And then at 100, this plateau we'll label as D. And then finally, we'll call this section E. This is called a phase graph. And we're going to try to make sense out of each section of this graph. We have 3 sections where there is a temperature change. If I'm adding heat, the temperature is increasing. There are 2 sections where the temperature is constant. And so we want to know what's happening at these different sections of the graph. Why is there sometimes a temperature change and sometimes no temperature change? So at A, C, and E, when the temperature is changing, the heat that's being added from your hot plate or your Bunsen burner or wherever it might be, that heat energy is being used to increase the kinetic energy of the water molecules. Temperature is a measure of average kinetic energy. So if you are increasing the kinetic energy of the water molecules, you're just making them move faster, but they are all in the same phase. Let's put that down here. There is no phase change. All the molecules are in a particular phase, and we're just increasing the temperature. So for example, we're not total idiots here. If I go back to this graph, and this is a graph for water, by the way, I know that any temperatures below 0, the water is a solid, right? So like this section A, this should represent all temperatures where your substance is a solid. Anything below 0 for water. Between 0 and 100, section C. I am pretty familiar with the fact that water should be in the liquid phase. And anywhere over 100, we should be in the gas phase. So we are not doing a phase change. If I increase the temperature from like 40 degrees to 60 degrees, the water is still liquid. We're not changing the phase. We are just increasing the kinetic energy of the particles. We're just making them move faster. All particles are the same phase. So, for example, what is the difference between water at 40 and water at 60 degrees Celsius? The difference is the kinetic energy. So we could say something like at 60 degrees Celsius, particles have more kinetic energy. Or in other words, if they have more kinetic energy, they just move faster. However, we should also make note, though, that at 40 degrees, 40 degrees, not 4 degrees Celsius, at 40 and 60, both samples are liquid. Both samples are in the liquid phase. So if I were to increase the temperature, I would not do a phase change. No phase change. We are just increasing the kinetic energy of the particles. We're making them move faster. No phase change. Okay, so anytime you see the temperature change, you are changing the kinetic energy of the particles. But what about section B and D of the graph, where the graph went flat? I mean, you kept the sample on the hot plate, so heat was still being added, but it's being used for a different purpose. And now again, we are not total idiots. I'm familiar with 0 degrees Celsius in reference to water. At 0 degrees Celsius, this is your melting. And at melting point, if I'm increasing in energy, it could also be my freezing point if I'm decreasing in energy. And at 100 degrees, if I'm increasing in energy, this would be like my boiling point. Okay, so I'm not a total idiot. I am familiar with those temperatures in reference to water. But obviously, if you're melting or boiling something, you're still adding energy. So why is the temperature stuck at 0 or 100 for quite a period of time? The energy that's being added, this is really important. It's used to overcome the intermolecular forces that hold the particles together. We're doing a phase change. And a phase change does require energy. but it's not being used just to make the particles dance around faster. That would be kinetic energy, and then we would see the temperature change. Why do we need energy for a phase change? Because we need to separate the particles, and they're held together by these attractive forces. So we need to use this energy for a different purpose. We need to overcome or separate the intermolecular forces, the molecular glue that's holding the particles together in order to change phase. So think about it like this. If I have a solid, the particles are packed pretty tight together. Here's my solid, my ice cube, or whatever it might be. So the energy first gets absorbed by the outer particles, and what I want to do is break whatever this is, this attractive force that's holding these particles together. I don't want to break the bonds. If this is water, I do not want to break the hydrogen-oxygen bond within the molecule. I want to separate the intermolecular forces that are holding the particles together in the solid phase. And so I add energy and boom, this particle escapes the solid crystal. And that happens to all the particles on the outside of your sample first. So these guys, all these particles on the outside. And this guy gets the energy, this guy gets the energy. These guys on the outside get the energy first. And so you start to see liquid forming in your beaker. The outer particles are melting. They're absorbing energy. We're overcoming their intermolecular forces and doing a phase change. Now we are doing a phase change. Phase change. But now here's what's really interesting. The outer particles will melt, but the inner particles are still solid. So we whittle away at this ice cube layer by layer by layer. So the outer particles will turn into a liquid first. The inner particles are still solid. You will be stuck at the melting temperature until the entire sample has changed phase. That's why there's no temperature change for a while. We're going to stay at 0 degrees. The energy is being added to the sample to overcome all of the intermolecular attractions. And so again, we go layer by layer by layer. Once the entire sample has changed phase, now if I keep adding energy, we'll just increase the temperature through the liquid phase. Interesting. So for example, if I go back to my graph, at the melting point, we kind of mentioned this earlier, there will be an equilibrium. You will see both solid and liquid. Both phases exist at the same time when you are at 0 degrees. Now early on, like at this point in the graph, it's mostly solid and just a little bit of liquid. As I get toward the end of this phase change, most of the particles are liquid and there's a small sample of solid. But the energy is being used for the phase change, which means that we're overcoming intermolecular attractions. And we won't change the temperature until the entire sample has changed phase. Same thing happens up at the boiling point. At the boiling point, you will literally see in the lab both liquid and gas. If I watch a sample of water boil, which is kind of boring, but if you watch boiling water, there are both phases present. At the beginning of this change, it's mostly water, and I might start seeing a small amount of vapor. Toward the end of the phase change, there's not a lot of liquid water left. Your entire sample has mostly turned to gas. And again, once the entire sample has changed phase, then we can increase the temperature of the gas particles. Interesting, huh? We need to recognize what is happening at each section of this graph in terms of the arrangement and kinetic energy of the particles, what phase is present, and what's happening to the particles. There is constantly energy being added. It's just being used for a different purpose depending on if we are doing a phase change or if we are just increasing the kinetic energy. Now we could also do this in the opposite direction. So we could have something that looks kind of like this. So we could go boop, 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 boop. We could go in the opposite direction, where here I'm removing energy from my gas, and then this section would be condensation. So this is still gas. Here I'm just cooling the liquid. I'm removing energy, so the particles are moving slower. Then this section would be my freezing point. So freezing and melting will occur at the same temperature. The difference is just the direction of the energy flow. Am I adding energy or am I removing energy? And then finally, this would all be solid. Every substance, every pure substance will have a phase graph that is similar, but these plateaus will just be at different temperatures. So for example, this is specific to water. Water melts and freezes at 0, it boils and condenses at 100. But if I had an unknown substance and they gave me the graph and they just said, hey, what is the boiling point of this unknown substance? It's the temperature of your second plateau. So every substance will have a very similar shaped graph. These temperature ranges will just be a little bit different. We call these phase graphs. We're going to try to recreate one in the lab. It's going to be great.